All right, we are back for day 20 of Advent of Code. Here we go. Okay, it's a grid. What is it asking us? How many cheats would save you 100 picoseconds? Okay, so you can cheat, I guess, to get through walls, presumably? Yeah. Disable collision for up to 2 picoseconds, so you can pass through walls. Okay. I see. Interesting. So this is once again a grid problem. The search. What is it? How many cheats would save you at least 100 picoseconds? Picoseconds. Very strict. Exactly once. Okay. It says exactly once, but you have multiple cheats. Fine. So what we care about is the shortest path. So we are going to need... technically, a breadth first search would work here, but I'm just going to pull out my Dijkstra's. Cool. So we have our grid, and then let's get our starting position, our ending position. This, and then this. Okay, and then the start is going to be just this. Let's write our adjacencies function. And then, so I guess, okay, technically our state here is going to have to include the number of cheats that we have done. How do I want to do this? Okay. Yes. So what we're going to do is we're going to set an allowed. And basically we'll represent this as the number of cheats we've used so far. And for GXY, I guess we also need another bool to indicate if we're currently phasing out of a cheat. So this is a little bit nasty, but if C is less than allowed, then we are allowed to like cheat one more time. If we cheat one more time, well, let's get to that when we get to that. So first we do this. Check all 4 adjacencies. We are going to need to check if we're in bounds here because you can phase through walls. Okay, and then now, if it's empty, then this is just fine. We can go to this new state just fine. The new state will involve we'll use the same number of cheats, and we are not currently phasing through a cheat. If it's a wall, technically we need a distance too. It's just the way I have this set up for Dijkstra's. If it's a wall, then we can only go there if we have not yet used up all of our cheats. And then also, we cannot be, so the start will actually be this, 0 cheats, false. We can't be currently finishing a phase. Basically, because we need to be like back in reality, we're not allowed to, I don't think we're allowed to chain multiple cheats together. So let's make sure we handle that. And that's what this last bool here is for, which is kind of annoying. So, and not Q, then we are allowed to move on to that square with using 1 extra cheat and setting Q. Cool. I think that's just fine then, right? So now we have our adjacencies, and the question is, so once we get here, then and then let's try this. So if nothing is allowed, then what's the optimal distance? Nothing is allowed. Okay, well, I have a bug. And y, and x, and y. Oopsies. Am I not setting these correctly? Oh, cannot do this. Okay, fine. Problem solved. Can't reuse n. Okay, and then if we allow some cheats, let's make sure that this number goes down. That went down way too much, I think. Maybe it didn't. Maybe it's fine. Well, anyways, so we'll do this, and then we return the distance. And now the question is, this went down so very fast. That makes me very suspicious. Why don't we print the final state over here? Yep, using one cheat. Do I really? This feels so weird. Oh, how many cheats would save you this? So you have a, oh, shoot. Okay, I misunderstood this. That is unfortunate. It's asking how many distinct cheats you can take that would work. So I guess one thing you can do is you can just express a cheat as like deleting a singular wall. So we're gonna keep allowed at 0. And I guess we'll just try deleting single walls. We still need to do this. But this is going to be... Wait, is deleting a wall, single wall correct, actually? I'm not 100% confident it's correct, but I think I just need to try it because it's faster, right? Okay, so first, and then if solve less than, or base minus solve is greater than or equal to 100. Let me make sure we put this back. I don't want the prints anymore. Although they shouldn't be slowing me down that much. Do I have PyPy in here? Well, I guess we'll find out. I shouldn't have any infinite loops, but how big is this grid? How far did we get? Not very far. That's pretty slow. I guess we just let it keep running. How's leaderboard doing? Leaderboard is full for part 1. This is really slow. Yeah, I knew when I spread this exactly once, it like felt inconsistent with my interpretation of the problem. So, but I guess it only makes sense if the number of adjacencies of a tile is at least 2. So I could prune a little bit. And pruning shouldn't matter, but needs to be at least 2. Then we can consider it. Oh, whew. I was worried about that because I was worried my print suppression would suppress the answer. But I do have, this is print C, which should override it. So it should just like print regardless. How much faster is this printing? A little bit faster. We won't see anything in this terminal until we see the output. There's the output, 1463, rank 148. Okay, that's still pretty high, surprisingly. Find the best cheats using updated cheating rules. Okay. Many more cheats are possible. At most. What does it say at most? Oh, interesting. I am not sure how to really approach this. All that matters are the start and the end positions of the cheat. Brute forcing all of those is not going to be possible. So you want to modify the search algorithm to sort of get this for you, I think. And now I'm not really sure. Oh, well, a thing we can do, still only end when the program is on normal track. Yep. So you can find all distances from the start, all distances from the end, and then you can sort of try it. Then you probably can brute force all cheats. Not like quite. But maybe. Yeah, why don't we try this approach? So let's generate distances from the start and distances from the end. How's leaderboard doing? Do I really need to rush on this? It might be leaderboardable, but it's kind of unlikely. I feel like this will take me a while to write. Yeah, so let's get distances from both sides. Let's see. Let's just do dists from a starting location. And I'm going to change this because it's probably was slowing down my code a little bit, at least, having this complicated state that was not really being used whatsoever. So it's just going to be this. This is going to be regular adjacencies. It doesn't actually matter how efficient this is. This is just going to run once, but whatever. Okay. So, and then now what we'll do, this should be a starting, I already have SX and SY being used, so I don't want to ever use those. I guess it's not a big deal, but, and then this should just give me distances to everything. So I think we're just going to do none of this. And then when we're done, we'll just return dists. No. Don't need this anymore. Okay. Oh. Fix that. Gotta fix that as well. I shouldn't bother trying to update that code. Okay. Should be 0. Yeah, I don't really put this in dists, which I probably should. Okay. This should be the same thing because it goes backwards. Okay, fine. So now what we do, This is not too hard because okay. So let's do. I'll leave this intact just for later. From start, from end, and then now for every position here, we could consider activating our cheat. So if you activate it here, then the range of tiles you can reach is pretty straightforward. This still feels like it's going to be really slow. But anyways, I guess we'll do it anyways. I'll write the dumb thing first. And then we consider everything from the end as well. And then this cheat is valid if and only if and x minus x and y minus y is less than or equal to 20, I think. 20 picoseconds. Is that right? I'm just thinking about off by ones. Yeah, I think that's right. And in this case, what we're going to do, if plus the distance, we just like take a straight line there from end, and x and y, is, what is the optimal? I guess, yeah, this. Is less than or equal to opt minus 100. This. This should work, but it should be pretty slow. Oh, that was pretty fast. 115, just barely missed it. Oh, man. Okay, that was a pretty cool problem. I'm wondering if there was something better than this. I was a little surprised at how fast this was, but I guess it's doing like, let's check, from start. Huh? Oh, I didn't run this here. I wonder how fast it is not in PyPy. Well, I just want to check the length of these two things. Okay, it is pretty slow not in PyPy. Maybe part of it is just that this is like a really tight loop and it's like not doing that much work, and PyPy like gets you a lot with that. Just, I guess I can't really tell how far it was, but yeah, I was worried about doing something that's like on the order of this squared, which is in fact what I am doing. That's like kind of a lot of work to do, but it's not like a ridiculous amount of work. What we are doing inside the loop is pretty straightforward and simple. So, but yeah, I guess I'll go ahead and explain the problem now. So what the problem is, yeah, we're given this grid. We're once again asked to make it from start to end. But the catch is we are allowed to cheat once, and when you cheat, you get to basically phase through a wall. So for 2 time steps, you get to not worry about the walls. 2 really lets you go through like a 1 thick wall, or I guess they say 2. It's technically like ignoring it for 1 step, and then you need to be back on solid ground in the next step, is sort of what they were saying. Yeah, and it asks how many distinct cheats are there that you can do, where a cheat is like, I assume it is a wall and a direction, and not just a wall. Oh, wait. Is it possible for these things to be different? That's actually a good question. I'm kind of curious. I always get distracted when I'm explaining the problems like this. So for there to be 2 different directions for you to be able to cheat through a wall, it would have to be like this. Oh, I think the problem might have been vague or weak test cases or something like that. If you have a case like this, are there 1 or 2 valid cheats here? Although these are valid cheats that let you make it to the end. Yeah, I mean, you can trivially transform this into the actual input. So I should finish explaining the question first. Yeah, it asks how many distinct cheats there are, whatever that means, that would save you at least 100 steps. Yeah, and the way that I did this was I tried all possible. So initially I just completely misunderstood. I thought you could cheat up to a certain number of times. So I wrote like a fancy state such that it would like track the number of times you cheated so far. And yeah, that was not at all what I was asking. I was asking for the number of distinct cheats you could do, and you could only cheat once per time. Distinct cheats you could do that would save you at least 100 steps. Yeah, and the way I ended up solving it is I just ended up trying like one at a time to remove each wall and seeing if when I remove that wall, is the new best distance better than more than 100 better than the previous best distance. Yeah, and that worked. So the thing I'm unclear about is in this case you can either go down and then right and then phase through the wall like this, or you could also like go to the right, phase through, and then phase through down. Either way, you are like, or you can come from the other direction as well. And these all result in like the same distance. So you can imagine that like if you don't do this, the only best path is like really, really bad. I'm not going to draw out like a length 100 path here, but imagine that the only other path was like pretty bad, and it did get you to the end. But like however you take the cheat here, it is like better. Does this count as one cheat or more than one? My code certainly would have counted it as one. I'm not sure what they wanted it to count as. And I don't know if it really matters if their grid is like, if your grid always has like, if it doesn't have like diagonal-ish walls, that's not like really the right way of saying that, but as long as it doesn't have patterns like this, I think it's fine to not worry about this. No, that's actually not true, because you could equally have just had what was I thinking here? If it was like this, then there's technically no like diagonal walls. I don't know. Do you like count this as a diagonal wall? I feel like there's ways to make this. I feel like you don't count that. And there's ways to make this such that it's like pretty ambiguous. But I assume that it is distinct by by the wall. Oh, no, it says uniquely identified by the start position and end position. So it's not vague at all. But what I did is not really quite right, I think. Maybe. That's a little surprising. Yeah. I wonder if that was true of everyone's input or not. Well, anyways, I think part 2 is kind of interesting, so I'll talk about part 2. Part 2 says, oh, actually, you can cheat for most 20 seconds, or picoseconds, which is like time steps, not just like 2. Now, how many cheats are there that save you at least 100 seconds, or picoseconds or steps? Again, it is like uniquely identified by its start position and end position. And for this one, the way I approach it is like a little bit more interesting. First, I do like I don't technically do BFS, I do Dijkstra's, but a BFS is like sufficient here because in this grid, all adjacencies are like distance 1. But you basically do like a breadth first search out from start to get distances to every grid node. And then you also do BFS out from ending to get distances to every grid, from every grid node to the ending. So because this graph is like undirected, you know that if it takes you, if you start it at the ending and it takes you 20 steps to get here, then you know if you start here, it takes you 20 steps to get to the ending. And now what you can do is you can take any 2 positions and ask yourself how much, like you can very quickly answer the questions of the form, how much time would it save me if I took a cheat to go from this position to this position? Because you already have stored in this dictionary of distances how long it takes you to get from start to here. You know how long it takes you to get from here to the ending. And because in the cheat you just phase through walls, you very quickly also know how fast it is to get from here to here. It's just like the absolute differences. Yeah, and so that's exactly what I wrote. I literally try all possible positions to like all possible starting cheating positions and all possible ending cheating positions, and I just ask, first of all, can I cheat to get from this position to that position? Like, are they actually close enough physically? Then I ask, okay, well, if I were to take this cheat, what is my best distance? And is it at least 100 better than the previous optimal? And if so, then that's my answer. So, and yeah, then that's the whole solution. I was a little surprised that this ran so fast, but I guess with PyPy, it does run pretty fast. Mostly I was worried because this is on the order of like 140 squared, like the number of starting positions, because this grid is 140 by 140. And this is also in the position of 140, or on the order of 140 squared. This should be like the same length exactly. So altogether, this is like 140 to the fourth, which is like starting to get a little sketchy. Of course, 140 to the fourth is actually like quite a bit larger than the actual number, because less than half of the grid cells, I think, actually have. I can check that actually. Yeah, just less than half actually have a empty space that you can get to. So it's a little bit better than 140 to the fourth. It's like it's more like 70 to the fourth, which is still large but pretty reasonable. I guess it's more than that. Oh, sorry, not 70 to the fourth, because it's 140 times 140 over 2, not 140 divided by 2 squared. Anyways, the point is, it is surprisingly efficient enough to just do it this way. If it wasn't efficient enough to do this way, I did have one more idea, which is you imagine that this step prunes out a lot of things. Like when you're trying all possibilities, just a lot of the time you will happen to like say, oh, what if I were to cheat from the top left corner to the bottom right corner, or things that are like equivalently far away? And those are just like not interesting because you know that you actually can't cheat for that distance. So rather than do a full iteration here, you could try and do something like, what was I thinking here? I was thinking you could do like for offset x in range like minus 20 to 20, and for offset y in range minus 20 to 20. This is probably not actually even the best way, but you basically like would consider only a grid centered around the start x and y. This like is better because you don't consider everything. It's worse because you do end up having to like loop through and check the like wall grid cells. So it's like not actually clear how much better it would be. I think this is like 40 by 40. You're having to consider an entire 40 by 40 area instead of half of 140 by 140 area. So yeah, it probably is substantially better to do it this way, actually. You could also do even better, which is because of the way the cheat works, it's actually like L1 distance, like Manhattan distance from a given point. So if we were to go like straight right, that's like distance 20. So this is like a cheatable distance. Straight down is a cheatable distance. But then it's not like Euclidean distance where you could go like, I don't know, like a circle or something. You can go exactly, let's draw this more to scale. There we go. You can go exactly 10 units in this direction, 10 units in this direction, or any combination thereof. So you end up getting like, this is the set of walkable locations that you can reach from. And a mathematician would call this the L1 ball, because this is like the set of all points that is reachable within distance 20 under the metric L1, where L1 is like the distance metric defined as Manhattan distance, basically. And yeah, so if you do this thing, this offset thing, you end up having to consider this entire range, and you like quickly disqualify these points. It would be possible to do a loop that is like, consider it this way. That's like if you could loop offset x from this range. So this side length here is notably not going to be 20. It is going to be, it's not going to be 40, which is what this one is. It is going to be, what, 40 over root 2, I think, is that right? 20 root 2. Yeah, so this lets you like save on a moderate amount. You get to only consider this much. But yeah, this is just like kind of annoying though to actually do the loops this way. So I don't think I've ever written something like that way. I normally just just like take the whole square and quickly disqualify these points. And this is like a factor of 2 slower, but it's not really a big deal. Yeah, I guess that's pretty convincing for why not to bother. It's only a factor of 2. So anyways, yeah, I definitely went off on like a pretty long tangent here. I think the core idea of like running 2 graph searches and then using these cache distances to do something quickly is actually like reasonably common in some algorithmic questions, and it's pretty cool. It's a neat little trick. So I wanted to at least explain that. But yeah, that is all I have for day 20. I will see you tomorrow.